Welcome to our geometry journey, where we explore fascinating properties of circles. Today, we will learn about a fundamental property. Drawing a perpendicular from the center of a circle to a chord always bisects that chord. Imagine the circle on your screen, with center O and a chord AB. When we drop a line from O perpendicular to AB, it hits AB exactly at its midpoint M. This means the two segments MA and MB are equal in length. To picture this, think of folding a paper along the perpendicular line through O. The chord's two halves line up perfectly. This all comes down to symmetry. Circles are perfectly symmetrical shapes, and this property helps us understand distances and angles within them. Look at the figure on your screen. Why do you think the perpendicular from the center hits the chord exactly in the middle? We will soon prove this with right triangles and congruency, after observing this neat symmetry. This theorem, though simple, is powerful, and forms the basis of many geometric constructions and proofs involving circles. So, let's start by observing, and then proving this exciting theorem. Let's dive into the geometric proof to understand why the perpendicular from the center bisects the chord. Consider a circle with center O and chord AB. We've drawn OM perpendicular to AB, meeting AB at M. To prove OM really bisects AB, meaning MA equals MB, we join points O to A and O to B, forming two triangles, triangle OMA and triangle OMB. Notice that OA and OB are radii of the same circle, so they are equal in length. The segment OM is common to both triangles. And AM and BM are the two halves of chord AB, which we are trying to prove equal. Our aim is to show triangles OMA and OMB are congruent. Because OM is perpendicular to AB, angles OMA and OMB are right angles, that is, 90 degrees, with two sides and the included right angle equal, by the RHS, or right angle hypotenuse side congruency criterion. The triangles are congruent. Consequently, all corresponding parts of these triangles are equal, so MA equals MB. That means the perpendicular from the center not only meets the chord at right angles, but also cuts it exactly in half. This proof illustrates the beautiful symmetry inherent in circles, one of geometry's elegant secrets. Often in mathematics, the converse of a theorem can be equally enlightening. Previously, we proved that if you drop a perpendicular from the center of a circle to a chord, it bisects the chord. Now, let's ask the reverse question. If a line from the center bisects a chord, is it necessarily perpendicular? This is called Theorem 9.4. It states that if a line through center O bisects chord AB at point M, such that AM equals MB, then this line OM is perpendicular to AB. How do we prove this? Like before, we will join OA and OB, the radii of the circle. By examining triangles OMA and OMB and using congruency criteria, we find that the angles at M are equal and add up to 180 degrees. This means each angle must be 90 degrees. Thus, OM is perpendicular to AB. This logical symmetry makes our understanding consistent and enriches circle geometry. You are encouraged to try this proof yourself with diagrams and check if this holds true in all cases. Before we delve deeper, let's understand a fundamental geometric idea: the distance of a line from a point. Imagine a point P situated anywhere above a straight line AB. If you draw several line segments from P to points on AB, most will be slanted. The shortest of these is special. It's the perpendicular dropping straight from P to AB, labeled PM. This PM segment forms a right angle with AB, meaning it's like the corner of a book, perfectly square. In fact, PM is the single shortest distance from P to the line AB. Any other segment is longer. Now picture this in a circle. Look at the picture. If chords are drawn inside the circle, longer chords are observed to be nearer the center, while shorter chords lie farther away. The longest chord, the diameter, even passes right through the center, so its distance from the center is 0. This relation gives us a beautiful insight, connecting chord length with how close it lies to the center. As we explore more, you'll see how these ideas prove vital in understanding circle geometry. Let's observe some powerful examples using perpendiculars from the center of a circle. Look at the picture. Each shows chords A, B, and CD inside, with perpendiculars OM and ON dropping from center O to these chords. Notice that OM and ON are not just any lines. They are perpendicular to chords AB and CD, and thus form right angles at points M and N. Here, M and N are the midpoints of the chords. So, these perpendiculars bisect the chords. This arrangement reveals a key relationship. If two chords in a circle are equal in length, then the perpendiculars from the center to these chords are also equal in length. In other words, equal chords are equidistant from the center. When applied to congruent circles, circles exactly the same size, this property still holds when considering equal chords. This symmetry is not just elegant. It is useful in geometric constructions and proofs. It also mirrors practical situations, like gears of equal size needing equal spacing. Keep this idea in mind as we proceed. The geometry of circles offers elegant rules tying together lengths and distances. One such rule, Theorem 9.5, tells us equal chords in a circle, or in congruent circles, are equidistant from the center or centers. What does this mean? Think of two chords inside the same circle that are exactly the same length. When you drop perpendiculars from the center of that circle onto these chords, each perpendicular segment will be the same length. These distances represent how far each chord is from the center. The magic of this theorem is in how it links equality in chords to equality in distances, revealing the uniformity and symmetrical nature of circles. This theorem has a converse too. If two chords are the same distance from the center, they must be equal in length. This relationship helps solve many geometry problems about circles, chords, and distances, making it a fundamental piece in your mathematical toolbox. Let's verify the converse of Theorem 9.5 through a hands-on activity. Picture a circle with center O. Draw two line segments, OL and OM, inside the circle such that OL equals OM in length. Now, from these points, L and M, drop perpendicular chords P, Q, and RS respectively. When measured, these chords turn out to be equal in length. By repeating this for various pairs of equal length segments, OL and OM, the chords P, Q, and RS, drawn perpendicular to them, remain equal. Thus, this exercise confirms that chords equidistant from the center of a circle are equal in length. This property deepens our understanding of circle symmetry and helps in many geometric proofs. Such exploration strengthens not only your skills, but also your intuition about geometric concepts, which is invaluable in mathematics. Synthesizing our previous explorations, Theorem 9.6 states, if two chords lie at the same distance from the center of a circle, then these chords must be equal in length. This theorem captures an essential aspect of symmetry within the circle, emphasizing that equal spacing from the center implies equal chord lengths. It complements the earlier theorems we have covered, such as the perpendicular from the center bisecting chords, and equal chords being equidistant from the center. Together, These theorems serve as powerful tools to solve challenging problems involving chords and distances in circles. By mastering these, you are laying strong foundations in circle geometry, which are applicable to more advanced mathematics and sciences. Let's look at a compelling problem involving chords intersecting inside a circle. We have chords AB and CD intersecting at point E. Through E, a diameter PQ of the circle passes. The problem tells us the angles these chords make with the diameter, angle AEQ and angle DEQ, are equal. Our task is to prove that the lengths of these chords AB and CD are equal. How do we approach this? First, we'll draw perpendiculars from the center O to each chord, creating segments OL and OM. These perpendiculars help us explore distances from the center to the chords, a crucial element in solving equality problems. By examining triangles created via these perpendiculars and the given equal angles, we'll work toward proving that OL equals OM, which leads us to the conclusion about the chord's equality. In the next slide, we'll continue the solution with detailed steps. Continuing from our previous slide setup, let's complete the proof that chords AB and CD are equal. Step 1. Consider triangle OLE. We know that the sum of interior angles is 180 degrees. Given the right angle at L, we calculate angle LOE as 180 degrees minus 90 degrees minus angle LEO. Step 2. Using the given equal angles, angle AEQ equals angle DEQ, and properties of the figure, angle LOE simplifies to 90 degrees minus these equal angles. Step 3. Similarly, angle MOE in triangle OME matches angle LOE. Step 4. Examining triangles OLE and OME, EO is the common side. Angles LEO and MEO are equal, and angles LOE and MOE are equal. Step 5. With two angles in the included side equal, by the ASA, that is angle side angle, congruence criterion, triangles OLE and OME are congruent. Step 6. From this congruence, sides OL and OM are equal. According to earlier theorems, equal perpendicular distances from the center to chords mean the chords themselves are equal. Therefore, we conclude AB equals CD, exactly what we wanted to prove. This elegant proof showcases how combining angle properties, congruency, and chord distance relations solves complex geometric problems. Now that we have explored the theory and seen examples, it is time to practice some problems to strengthen your understanding. First, try drawing a circle with a chord XY that does not pass through the center. Drop a perpendicular from the center O to the chord, meeting at point M. Can you prove that this perpendicular bisects XY? Remember the theorems we covered. Next, given two equal chords in a circle that are 10 centimeters from the center, with the radius 13 centimeters, can you calculate their lengths? Here is a hint. Use the Pythagorean theorem on the triangles formed. Third, prove that if two chords are at the same distance from the center, they are equal in length. This is an application of Theorem 9.6. Finally, if chords PQ and RS are 4 centimeters and 7 centimeters from the center respectively, which chord is longer? Consider the inverse proportionality between the distance from the center and the chord length. Work through these problems carefully and refer back to the key theorems we have learned. You will find the solutions logical and rewarding. Let's review the solutions. For the first problem, by Theorem 9.3, any perpendicular from the center to a chord bisects the chord. This means M is the midpoint of XY. In the second problem, we use the Pythagorean theorem. Half the chord length equals the square root of radius squared minus the distance squared. So half the chord length is the square root of 169 minus 100, which gives 9 centimeters. Multiply by 2 for the full length, which is 18 centimeters. Third, chords equidistant from the center are equal in length, according to theorem 9.6. So AB equals CD. Fourth, the chord closer to the center is longer. So PQ at 4 centimeters distance is longer than RS at 7 centimeters. To sum up, these problems reinforce how perpendiculars from the center and distances determine chord lengths. This grounds your understanding of circle geometry and prepares you for more complex applications.